Today I would like to discuss the crystal field stabilization energies. Myself Dr. Digna Varghese. Field stabilization energies or CFSE. Before we are going to discuss the crystal field stabilization energies, we have already studied the crystal field splitting in various fields like octahedral, tetrahedral and planar complexes or fields. In that case, the 5 d orbitals are splitted according to the ligand field. Actually, they are splitting in order to attain the stability. Okay, if you have not studied the crystal field splitting in detail, please go through the link given in the top or in the description box. So now we are discussing crystal field stabilization energies. The crystal field stabilization energy is the stability that results from placing a transition metal ion in the crystal field generated by a set of ligands. Crystal field stabilization energies arises due to the fact that when the d orbitals are split in a ligand field, some of them become lower in energy than before with respect to a spherical field known as the barycenter, in which all the 5 d orbitals are degenerate. So there is a net energy decrease is called the crystal field stabilization energy. So crystal field stabilization energy is the energy change relative to that of the hypothetical crystal field splitting, that is a spherical field or a barycenter. A consequence of crystal field theory is that the distribution of electrons in the d orbitals may lead to net stabilization, that means a decrease in energy of some complexes depending on the specific ligand field geometry and metal d electron configurations. It is a simple matter to calculate this stabilization since all that is needed is the electron configuration and knowledge of the splitting patterns in different fields. Here you can see the splitting pattern of octahedral field, tetrahedral field and planar field and the tetrahedral field. The 5 degenerate d orbitals on the central metal ion is shown here after approaching the ligand. So the d orbitals are degenerate but somewhat rise in energy. After that, it again splits due to the ligand field. It is only a hypothetical case. It is also known as barycenter or a spherical field. So crystal field stabilization energy is the energy change relative to that of the hypothetical crystal field. Here the hypothetical crystal field, this is the corresponding energy and the d orbitals again split into different sets according to the different geometry or different arrangement of the ligands around the central metal ion relative to the hypothetical crystal field. So the crystal field stabilization energy is the energy change relative to that of the hypothetical crystal field. We can calculate crystal field stabilization energy is the change in energy, that is delta E is equal to E ligand field minus E isotropic field. Isotropic field means the hypothetical crystal field. You can see here the energy change, that is delta O 10 dq in the case of octahedral. For the tetrahedral field it is delta T, and the tetrahedral field from the octahedral state it is again divided into 4 sets, and square planar it is again divided into 4 sets, but the energy change is different. So This is the crystal field stabilization energy value, that is the energy change related to that of the hypothetical crystal field. Now we are going to discuss the calculation of crystal field stabilization energy in octahedral field. We have seen that according to crystal field theory, under the influence of the six ligands approaching towards the central metal ion during the formation of an octahedral complex, the d orbitals of the central metal ion are split into two sets, that is T2G set, lower energy set, and EG set, higher energy set. The energy gap between the T2G set and EG sets are represented by the term delta O or 10 dq. The energy of T2G set is lowered by minus 4 dq or minus 0.4 dq or 2 by 5 delta O, while that of the EG set is raised by 3 by 5 delta O or 0.6 delta O or 6 dq. Thus, each electron occupying, which is related to the hypothetical degenerate d orbitals on the central metal ion. Thus, each electron occupying the T2G orbitals decreases by the energy minus 4 dq. Okay, while that going into the EG orbitals increases its energy by 0.6 dq or plus 0.6 delta O or plus 6 dq. And minus and positive signs indicate the respectively the decrease in energy or increase in energy of d orbitals caused by their splitting under the influence of the six ligands in the case of octahedral field. Okay, so here a formula used to calculate the crystal field stabilization energy in octahedral field, that is the number of electrons in T2G level into 0.4 delta O minus number of electrons in EG level into 0.6 delta O. Okay, that is gain in energy due to the electrons in EG orbitals, that is plus 6 dq or 0.6 delta O into how many number of electrons in EG level. Here loss in energy due to the electrons in the T2G level into 0.4 delta O. Therefore, the net change in energy is equal to, for a general configuration T2GX EGY, we can calculate crystal field stabilization energy is equal to minus 0.4 into number of electrons in T2G level, that is X, plus 0.6 into number of electrons in EG level, that is Y, into delta O. Here two cases arises. In the case of weak field ligands, those ligands which cause lower in energy. For the case of weak field ligands, for the case of D4 state, electrons will fill in this way: dx1, dyz1, dxz1, and go into the next stage dx square, y square 1 or dz square 1. Okay. In the case of weak field ligands, that type of ligands cause lower splitting of d orbitals. That is, delta O value is smaller compared to the pairing energy of the electrons. Okay, here weak field case delta O is smaller compared to the pairing energy of the electrons so that there is no pairing occurs and going into the higher level. Okay. Weak field ligands contain halogen, oxygen and sulfur as donor atoms. There is another case. In the case of strong field ligands, the same configuration for the same configuration D4, the electron fill in the T2G level. After that, it also again the electron fill the same T2G level and form a pair or pairing of electrons occurs in the case of strong field ligands because in this case the crystal field splitting parameter is high compared to the pairing energy. Okay, that types of ligands is known as strong field ligands. Strong field ligands contain carbon, nitrogen and phosphorus as donor atoms. So there are two types of ligand fields. One is strong ligand field and the second one is weak ligand field. In the case of weak ligand fields, the delta O value is small compared to the pairing energy of the electrons. In the case of strong field ligands, delta O value is high when compared to the pairing energy of the ligands. So in the case of strong field ligands, pairing occurs, while in the case of weak field ligands, no pairing occurs until it fills the Eg level in the half-filled configuration. After that, only pairing occurs. We know for a general configuration T2GX CGY configuration in an octahedral field, the crystal field stabilization energy calculated by the formula minus 0.4 into number of electrons in the T2G level plus 0.6 into number of electrons into T2G level into delta O. Here we can calculate for a D1 metal ion, the electronic configuration is T2G1. One electron is any one of the triply degenerate orbitals. Here it is in the dxy orbital. So it has an energy 0.4 delta O relative to the barycenter center of the d orbitals. That is minus 0.4 delta O. That is stabilized by minus 0.4 delta O relative to the barycenter center of the d orbitals. That is its crystal field stabilization energy. The complex can thus be said to be stabilized to the extent of 0.4 delta O compared to the hypothetical spherical field case. This quantity is termed as the crystal field stabilization energy. So, the crystal field stabilization energy for the D1 metal ion is minus 0.4 delta O. Now we are going to calculate the magnitude of delta O. Here you consider an example hexa aqua titanium 3 ion. It is a D1 complex. Titanium 3 plus is a D1 complex. The aqueous solution of titanium 3 plus and gives rise to a purple color. The purple color is the result of absorption of light and the promotion of the T2G electron to the Eg level. That means it's a simple DD transition. That is, the ground state configuration is T2G1 Eg0. After the absorption of light by the complex and the promotion of electron from the ground state to the excited state, that is T2G0 to Eg1. So the absorption spectrum you can see here, the maximum value at 20,000, the maximum lambda max at 20,000 centimeter inverse, and the corresponding energy is 243 kilojoule per mole of energy. So titanium complex, 3 plus complex, the aqueous solution gives rise to purple color. That the lambda max corresponding to this is 20,000 centimeter inverse. The calculation of the magnitude of delta O in such a way that delta O is equal to E light, that is energy of the light, that is equal to h nu, that we know. Lambda is equal to c by nu. Nu is equal to delta O by h. Okay. Here delta O is equal to light energy, that is equal to h nu. Lambda is equal to c by nu and nu is equal to delta O by h. Or we can write it in this way as delta O is equal to hc by lambda. That is lambda is equal to c by nu. So h is the Planck's constant 6.626 into 10 raised to minus 34 joule second. C is the velocity of light 2.997 into 10 raised to 8 meter per second, and into number of particles, that is 6.022 into 10 raised to 23 divided by lambda, that is corresponding to 492 into 10 raised to minus 9 meter, that is equal to 243 kilojoule per mole. That is the value of delta O. Delta O is corresponding to the energy of light, that is 243 kilojoule per mole. For a D2 metal ion, the electronic configuration is T2G2, that we know. And here the electrons are arranged in the triply degenerate ground state energy level, that is dx1, dxy1, dxz1. Okay. And crystal field stabilization energy for the D2 metal ion is 0.8 delta O, that is corresponding to the minus 0.4 into 2. Okay, minus 0.8 delta O. The magnitude is only given here for crystal field stabilization energy, that is 0.8 delta O. For D3 metal ion, the electronic configuration is T2G3. One more electron added to the triply degenerate T2G level in addition to D2 metal ion. Okay. Here 3 into minus 0.4, that we will get 1.2 delta O for the crystal field stabilization energy for the D3 metal ion. For D4 metal ion, there are two possibilities arise, that is T2G3 Eg1 or T2G4 Eg0. T2G3 Eg1 occurs if delta O less than P, that is a weak field or high spin condition, that we have already discussed. Here you can see for the D4 metal ion in high spin condition. Here delta O value is less than pairing energy. So pairing is not possible here. So after that filling in the half-filled configuration in the T2G level, the electron goes into the Eg level. Okay. So the crystal field stabilization energy for T2G3, that means 3 into minus 0.4 plus 1 into 0.6. So the total CFSE value for D4 configuration in the high spin condition is 0.6 delta O. D4 metal ion in low spin condition. Here the condition is delta O greater than P. That means pairing energy. It is a strong field or low spin condition. Here the delta O is high than the pairing energy. So pairing of electrons occurs, after that only it goes into the higher state. So D4 metal ion, T2G4 is the configuration. So T2G4 means 4 into minus 0.4, that will give
It is considered the
1.6 delta
D4
O
metal
for the
ion.
CFSE of
We know
D4 metal
there is
ion.
4 electrons. In the case of octahedral crystal splitting, the splitting is in a way that there is lower T2G level and higher EG level. In the case of T2G level, 3 electrons can be filled in a normal way, and the 4th electron can arrange in a down field or in up field, that is in a T2G level itself or in a EG level. Therefore, there is 2 possibilities in the case of D4 metal ion, that is T2G3 EG1 or T2G4 EG0. T2G3 EG1 electronic configuration occurs if the ligand field is a weak field or it is a high spin condition. That means the crystal field splitting is lesser than the pairing energy. In the case of T2G3 EG1, T2G3, there is 3 electrons in the minus 0.4 delta O stabilization energy, that is minus 0.4 into 3, that is minus 1.2, which is less than minus 0.6 delta O. Therefore, the crystal field stabilization energy for D4 metal ion in T2G3 EG1 configuration is 0.6 delta O. While in the case of T2G4 EG0, this configuration occurs if delta O is higher than pairing energy. This is because in the case of strong ligand field or in the low spin condition. Therefore, the 4 electrons occur in the T2G level, that is stabilized by minus 0.4 delta O from the barycenter. Therefore, 4 into minus 0.4 delta O is equal to 1.6 delta O. That is CFSE for D4 metal ion in T2G4 EG0 configuration is 1.6 delta O.
Here you can see the crystal field stabilization energy for the various configurations. For D1, we have already discussed both the weak field and strong field condition. Its CFSE value is same up to D3 configuration. After that, D4 configuration, there is for the weak field configuration 0.6 delta O and strong field configuration it is 1.6 delta O. D5, in the case of weak field it is 0, strong field it is 2. D6 configuration T2G4 EG2, the CFSE value is 0.4 delta O. For the strong field, no unpaired electrons, T2G6, therefore 2.4 delta O. In the case of D7, 3 unpaired electrons and here 0.8 delta O for the high spin condition. Low spin condition is about 1.8 delta O. For D8 configuration, in the case of weak field and strong field, same is the CFSE value, that is 1.2 delta O. For the D9 configuration, 0.6 delta O, that will be same for the strong field condition. D10, in both weak field and strong field, its value is 0 delta O. Calculation of crystal field stabilization energy in tetrahedral field. Here you can see the crystal field splitting diagram for tetrahedral field. The formula for the calculation of crystal field stabilization energy in tetrahedral field is that number of electrons in E level into 0.6 delta T minus number of electrons in T2 level into 0.4 delta T. For a general configuration, EXTY crystal field stabilization energy is equal to minus 0.6 into x plus 0.4 into y delta T. For a general configuration of a tetrahedral complex, that is Ex T to Y, we know E level is the lower energy level for tetrahedral field and T2 is the higher energy level. The crystal field stabilization energy is calculated by using the formula minus 0.6 into number of electrons in E level minus 0.4 into number of electrons in the T2 level. Here you can see the different configurations of tetrahedral field, the n configuration. Therefore, corresponding electron arrangement is given here and the number of unpaired electrons is in this column, and crystal field stabilization energy corresponding to each configuration is calculated here. For example, for the d5 configuration in the tetrahedral field, tetrahedral complexes are always high spin complexes. Here you can see for the d5 configuration 1 electron, 2 electron, and third electron, fourth electron, fifth electron. For the weak field case, delta value is less than the pairing energy of the electron. So these are high spin complex, but its CFSE value is 0. That is given here. For D8 configuration, the value is after filling 5 electrons in this way, and the sixth electron is given here, pairing occurs in the T2 level, and seventh also pairing occurs, and the eighth electrons. There are two unpaired electrons in the case of D8 configuration, and the corresponding value is that minus 0.6 into 4 plus 0.4 into how many electrons in the T2 level? Again 4. Okay. Therefore, minus 0.6 into 4 means minus 2.4 plus 0.4 into 4 means 1.6. Therefore, 0.8 delta T is the CFSE value for D8. Now you can calculate for the CFSE value for tetrahedral configurations. Field stabilization energy calculation in square planar fields. Here you can see the crystal field splitting pattern of square planar fields. The lower energy is dxy, dyz, dxz, and the next higher level is dz square. Next higher level is dxy, and the most highest energy level in this square planar complex is dx square, y square. In the case of square planar coordination is rare, that we know it is not common except for D8 metal ions. Among the D8 metal ions, the exhibiting square planar coordination are nickel 2, palladium 2, platinum 2, rhodium 1, iridium 1, copper 3, silver 3, and gold 3 complexes. In the case of D9 complexes, that is with copper 2 ion and silver 2 complexes, are occasionally found in square planar coordination. Okay, all non-square planar complexes D8 ions are diamagnetic because here for the D8 complexes the 4 electrons is within the dxy, dxz, dyz orbital, and for the dz square orbital there is again filled by 2 electrons, and for the dxy it is also filled by 2 electrons. 4 plus 2 plus 2, that is 8 electrons. This is the higher energy level that is vacant. In always All the square planar D8 complexes are diamagnetic. Some exceptional cases are also there because in this highest energy level, that is dx square y square energy level, is greatly destabilized. That means it has higher or greater repulsion and form a highest energy orbital that is greatly destabilized, and pairing in the dxy orbital is more favorable than placing an unpaired electron in the dx square y square orbital. Okay, so the calculation of CFSE value is like this. We are going to calculate the crystal stabilization energy in square planar complexes. We know the square planar D8 complexes are diamagnetic, and the electronic arrangement of 8 electrons in this way: dx is at 2, dy is at 2 electrons, dz square again 2 electrons, and dxy 2 electrons. Dx square y square orbital is vacant. Here you can see the splitting pattern of square planar coordination in xy plane. That is, here the delta O difference between the dz square value to d doubly degenerate dxz divisor orbital is minus 0.51 delta O. Therefore, the CFSE in square planar complexes 4 electrons in the ground state into minus 0.51 delta O. Here there is a relative energy difference between these two levels, that is dxy and dz square, that is about 0.43 delta O. Therefore, 2 electrons into dz square into 0.43 delta O, and here is again energy difference value corresponding to dxy orbital, that is 0.23 delta O. Okay, that is 2 into 0.23 delta O. So the CFSE for a diamagnetic square planar D8 metal complex is calculated by using the formula CFSE is equal to 4 into minus 0.51 delta O, 2 into minus 0.43 delta O, plus 2 into 0.23 delta O, plus P. P means pairing energy, that is equal to minus 0.244 to minus 2.44 delta O plus P. P is the pairing energy correction. Here the pairing energy correction is also included because we know in a free D8 metal ion there is 2 unpaired electrons, but a square planar D8 complex, it has no unpaired electrons. Here we are discussing some important uses of crystal field stabilization energy values. That is, first one is used for the computation of lattice energies. Second one is the predicting the structure of spinels. And the third one explains the stabilization of oxidation states of the metal ion. And the fourth one, the stereochemistry of complexes. So these are the applications or uses of crystal field stabilization energy values.
The first use
The
of
first
crystal field
use of crystal
stabilization
field
energy
stabilization energy
value
value
is
is
the
the
computation
computation
of
of
lattice
lattice energy.
energies.
We know
We
the
know
lattice
lattice
energy
energy
is a
is
measure
the
of the
measure of the
energy
energy
released when
released when
ions are
ions
combined to make
are
a
combined
compound.
to make a
It is
compound.
actually the measure of the cohesive
Actually,
forces
it is
that
the
bind
measure of
ions.
the cohesive forces that bind
We
ions.
know the lattice energy
Lattice
value
energy is
is
deduced
deduced
from
from
the
the
Born-Haber
Born-Haber
cycle
cycle
that we
that
have
we
already
studied in
studied in
UG
UG
classes.
classes.
Why lattice energy
Why
value
lattice
is
energy is
important? It is
important?
relevant to
The
many
value of lattice
practical
energy is
properties
relevant to
including
make
solubility, hardness,
many
and
practical
volatility.
properties like solubility, hardness, volatility, etc.
Now we are going to predict the lattice energy values from crystal field stabilization energy value. This prediction is accurate for some ions such as sodium ion, potassium ion, calcium ion, manganese 2 and zinc 2 ion. But this value is not accurate for some other ions such as chromium 2, iron 2, cobalt 2, nickel 2 and copper 2. The lattice energies of the halides from calcium halide to zinc halide, we are expecting the values increases from calcium to zinc in a, according to Bond-Lange equation. But the expected increase in lattice energy based on Bond-Lange equation. Here you can see the Bond-Lange equation, that is V is equal to minus Na mz plus minus QE square by 4 pi epsilon 0 R0 into 1 minus 1 by N. We know according to Bond-Lange equation, one can expect a smooth increase in lattice energies from calcium to zinc, that we go from left to right in the plot, but due to decrease in ionic radius from calcium to zinc. So we are expecting more lattice energy like this. But the accurate value of the prediction of lattice energy by the Christoffel stabilization energy is not so similar to that curve. As anticipated, a smooth curve is not seen here. Only a straight line observed for calcium, manganese, and zinc to lie on the straight line. The deviations from this line are maximized in two places. So we get, instead of a straight line for most of the ions, here you will get, or you can see here, a double hump shaped curve. Okay. Calcium, remember calcium, manganese, zinc halides lie on a straight line. For calcium 2 plus, we know it is a D0 configuration. For calcium, manganese 2 plus, we know it has a D5 configuration. For zinc 2 plus has a D10 configuration. For D0, D5 and D10 configurations, the crystal field stabilization energy value is 0. Okay. So it obeys, or we can predict from the crystal field stabilization value. Sorry, we can predict the lattice energy values from the crystal field stabilization value. We get a smooth straight line curve for these ions. But we get a maximum deviations for vanadium and nickel chloride case. For vanadium chloride, we know its configuration, or the oxidation state of vanadium is +2, and it has a D3 configuration. And for nickel 2 plus, it has a D8 configuration. These two values have the maximum CFSE value, that is for D3 configuration 1.2 delta O, and for D8 configuration 1.2 delta O. So for the maximum CFSE value, maximum deviation from the straight line. Okay. And there are other cases for the titanium 2, chromium 2, iron 2, cobalt 2, copper 2, etc. In these cases, for titanium 2, that is D4 configuration, D2 configuration, chromium 2, that is D4 configuration, for copper 2, D9 configuration, and cobalt 2 for D7 configuration, and so on. These values are in between zero point 0.6 and point somewhat less or equal to zero point 0.6 and zero point 0.8 delta O. Okay, so ions such as vanadium, which show high crystal field stabilization energy, like nickel 2 plus, other ions have the lattice energy values show significant deviation from the calculated lattice energy values due to its crystal field stabilization energy in a weak field situation. Now we are going to predict the structure of spinels from the crystal field stabilization energy values. Spinels are mixed oxides. They are named after the name of mineral spinel. Its molecular formula is MgAl2O4. The general formula of spinel is Ab2O4, like MgAl2O4. A2 plus and B3 plus are divalent and trivalent metallic cations. The general formula of spinel is Ab2O4. Remember, A and B are divalent and trivalent metallic cations. A and B can also be the same metal with different valencies, or it may be different. It can be also different. Remember, A and B can be the same metal with different valencies, such as in the case of magnetite. Its molecular formula is Fe3O4. It can be written like the general formula Ab2O4 as Fe2 plus Fe3 plus twice O4 2 minus. Okay. A and B can also be different, like the spinel MgAl2O4. Here, magnesium is the divalent one, aluminum is the trivalent metallic cation. In spinels, there are oxygen atoms. The oxygen atoms are arranged in a cubic close packed lattice that you can see in the picture of magnesium Al2O4. Each oxygen atom has 12 other oxygen atoms equidistant from other. Here you can see the red balls are oxygen atoms and blue balls are aluminum and green one is magnesium. Okay, so the oxygen atoms are arranged in cubic close packed lattice. Each oxygen atom has 12 other oxygen atoms equidistant from it. The holes between the oxygen atoms are of two types. First one is the octahedral holes and the second one is tetrahedral holes. Octahedral holes means that oxygen atoms surrounded by 6 other oxygen atoms. And second one is tetrahedral holes, that is each oxygen atom surrounded by other 4 oxygen atoms. In a spinel, there are one octahedral hole and two tetrahedral holes. Okay, remember, tetrahedral holes are always smaller than the octahedral holes. Spinels are classified into two types, normal spinel and inverse spinel. Here we are discussing normal spinel. Its general formula is Ab2O4. An example is magnesium aluminate, that is MgAl2O4. Here we know A atoms are divalent, B atoms are trivalent metallic cations. In the place of A, here is magnesium 2 plus. In the place of B, here it is aluminum 3 plus ions. The magnesium 2 plus ion occupy 1/8 of tetrahedral holes and aluminum 3 plus ions occupy 1/2 of the available octahedral holes. Magnesium ions occupy 1/8 of tetrahedral holes and aluminum 3 plus occupy 1/2 of the available octahedral holes. Oxygen atoms are arranged in a cubic close packed lattice and the cations A and B occupying some or all of the octahedral and tetrahedral sites in the lattice. In the case of spinel MgAl2O4, magnesium ions occupy 1/8 of the tetrahedral holes and aluminum occupies in the 1/2 of the available octahedral holes. Oxygen atoms are arranged in cubic close packed lattice. In the general formula Ab2O4, we can say like that A and B occupying some or all of the octahedral and tetrahedral sites in the lattice. The charges of A and B in the prototypical spinel structure are +2 and +3 respectively, that we have already discussed. This is the arrangement that would be predicted to be most stable in as much as it yields a coordination number of 4 for the divalent ion and coordination number 6 for the trivalent ion. We know in the magnesium ion occupies the tetrahedral holes. That means A atoms arranged in a tetrahedral arrangement. That means coordination number is 4 and the B atoms, that is aluminum, occupies the available octahedral holes. That means the trivalent cation, the coordination number is 6. What is an inverse spinel? Inverse spinel represented by B3 plus, A2 plus, B3 plus, O4 2 minus. All the A2 plus cations and half of the B3 plus cations are in octahedral holes. The other B3 plus cations are in tetrahedral holes. In the case of normal spinel, all the A cations are in tetrahedral holes and B cations are the 1 by half of the available octahedral holes. Here, all the A and half of the B ions are in octahedral holes and the half of the B ions are in tetrahedral holes. Here are some examples of inverse spinels: copper ferrite, magnetite, titanium zincate, tin cobaltate, magnesium ferrite. These are some examples of inverse spinels. Here copper Fe2O4 can be represented as Fe3 plus, copper 2 plus, Fe3 plus, O4 2 minus, in which A atoms are copper, B atoms are iron. In this case, A atoms and B atoms are the same iron but different oxidation states, and so on. Here you can see the magnetite structure. Oxygen is shown here by yellow balls, iron 3 plus shown here by tetrahedral sides by green color, and navy blue is the iron 3 plus in octahedral sides. Normal versus inverse spinel. For transition metal oxide spinels, the choice of the normal versus inverse spinel structure is driven primarily by the crystal stabilization energy of the ions in the tetrahedral and octahedral sides. The crystal stabilization energy values are greater for octahedral than for tetrahedral sides. Crystal field theory helps in predicting the structure of spinels. For spinels that contain 3D transition elements such as chromium, manganese, iron, cobalt, and nickel, the electron configuration is typically high spin because O2 minus is a weak field ligand. Example, magnetite Fe3. Now we are going to predict the structure of magnetite Fe34, whether it is a normal spinel or an inverse spinel. So consider the d-orbital energy diagram for Fe2 plus. Here you can see the Fe2 plus splitting diagram in an octahedral field, and its corresponding CFSE value is about 0.4 delta O, and in the case of tetrahedral field it is about 0.6 delta T. Since delta O is 2.25 times larger than delta T, the octahedral arrangement has a larger CFSE and is preferred for Fe2 plus. We are considering the d-orbital energy level diagram for Fe3 plus. The CFSE for Fe3 plus in the octahedral configuration, that is here D5 configuration, so its CFSE value is 0. For tetrahedral also its CFSE value is 0. So this particular ion, that is Fe3 plus ion, has a no preference for both the octahedral and tetrahedral holes because its CFSE value is found to be 0. So in Fe3 or 4, all the iron 2 plus ions occupies in the half of the ion, all of the Fe2 plus ions and half of the Fe3 plus ions are in the octahedral sites, while the remaining half of the Fe3 plus ions occupy the tetrahedral holes. That is, it's an inverse spinel and its structure is therefore represented as Fe3 plus, Fe2 plus, Fe3 plus, or 2 minus. We are going to predict the stabilization of the oxidation states of metal ions from its CFSE values. We know why certain oxidation states are preferentially stabilized by coordinating with certain ligands. You can see here the water can coordinate with the cobalt 2 plus and cobalt 3 plus ions to form the high spin octahedral complexes. You can see here that complexes are hexa aqua cobalt 2 ion and hexa aqua cobalt 3 ion. Water stabilizes the cobalt 2 plus ions and not cobalt 3 plus ions. Therefore, cobalt 2 plus complex is more stable than cobalt 3 plus complex because the fact that cobalt 2 plus is a D7 has configuration, its CFSE value is 0.8 delta O, and cobalt 3 plus is D6 configuration and its CFSE value is 0.4 delta O. So high CFSE value will be highly stable complex. So cobalt H2O6 2 plus is highly stable than cobalt 3 plus aqua complex. Now we are going to discuss the stereochemistry of complexes according to the CFSE values. Why copper 2 plus ions form square planar complexes rather than the tetrahedral or octahedral complexes? We know the CFSE values for copper 2 plus ion, that is D9 configuration in square planar configurations, values about CFSE values about 1.22 delta O. In an octahedral complex, for the copper 2 plus ion, the CFSE value is only about zero point 0.6 delta O, and for the tetrahedral configuration, the CFSE value is about 0.18 delta O. So higher the CFSE value, higher will be the stability of the complex, and the stereochemistry corresponding to the D9 configuration is square planar configuration. So copper 2 plus ions form square planar complexes more. Thank you for your attention.